welcome back. So, we were discussing about effective stress and effective strain. So, let me rewrite some of the equations that we discussed yesterday. So, if you are talking about von Mises, we talked about effective stress and we came to the relation that we are talking about stress. So, effective stress is equal to 1 over 2 sigma 1 minus sigma 2 whole square plus sigma 2. Remember we came to this form because this is also the form for the yielding criterion for von Mises. So, this is the effective stress in von Mises and the effective strain that we came to. We did not derive it again, we just wrote it down that this has been shown assuming that your incremental strains d epsilon 1 and d epsilon 2, d epsilon 3 are proportionate throughout. Then we get this two relation for von Mises condition. For Tresca also we said that there is effective stress and that effective stress is nothing but sigma 1 minus sigma 3. And we said that there is a particular reason why we have 1 over 2 over here. We will get to that again in a moment very soon. But before that, to complete the picture, let me also put down what will be the effective strain if we were to consider only the Tresca criterion, and it will be d epsilon 1. So, what it is saying is that in the Tresca condition, or if you are assuming Tresca criterion, then the effective strain depends only on one principal strain, but empirically this is not supported empirically. Therefore, what you will see is that this Tresca condition for, or the effective stress and strain under the Tresca criterion is not used very often, and what is used is von Mises criterion. Now, coming to the point on why we are using 1 over 2 and 2 over 3, we can understand the form of the equation. It has to be of the same form as our yielding criterion, but why do we have to have 1 by 2 and so on. Now, let us consider simple tensile condition or tensile test. Okay. So, in tensile test your sigma 1 is not equal to 0, sigma 2 is equal to sigma 3 is equal to 0, epsilon 1 is not equal to 0, and we can add the non compressibility rule, which is that not plus, by what I am trying to say is epsilon 1 plus epsilon 2 plus epsilon 3 equal to 0, and since epsilon 2 and epsilon 3 which are on the perpendicular or on the transverse sides, they will be of equal magnitude, you can show that epsilon 2 equal to epsilon 3 is equal to minus epsilon 1 by 2. So, this comes directly from this. So, if you have these two conditions, because we have the primary strain in one along the direction in which you are applying stress, in the other two direction because of the non compressibility. So, remember in simple tensile test sigma 2 and sigma 3, which are the stresses on the perpendicular direction, are 0, but not the strains on the other two direction. There is still some strain, and that is because there cannot be the material cannot get compressed, there has to be some amount of strain. You cannot or in this case actually if you keep elongating the material without it getting contracted on the sides, it would mean that the total volume is increasing, which is what we have forbidden. We had taken an assumption, and that is a valid assumption, volume does not change during plastic deformation, not in the range we are interested in. So, this is epsilon 2 to be precise. So, now what you will see is that if you put this value over here, what you will get is epsilon bar. Now put epsilon 2, epsilon 3 equal to minus epsilon 1 by 2 over here. So you will have epsilon 1 square plus epsilon 1 square by 4 plus epsilon 1 square by 4. So you have 2 epsilon 1 square by 4 and which is 1 by 2 epsilon 1 square, and this is epsilon 1 square. So that is 3 by 2 of epsilon 1 square, and that gets cancelled over here. So you are left with square root of epsilon 1 square. Therefore, effective strain comes out to be epsilon 1. So you see, in our simple tensile condition, epsilon bar is coming out to be equal to epsilon 1, which is the primary strain, although the other two strains exist, but in the effective strain is actually coming out equal to the primary strain. And since sigma 2 and sigma 3 are 0, you put it over here, and what you get is that sigma bar is equal to sigma. So we have two very important results over here. Your effective stress is same as the stress that you get in uniaxial tensile condition. Effective strain is same as the uniaxial strain or the strain in the uniaxial tensile condition, which means it has a very strong implication. If you can understand the meaning, you will be really surprised what it is actually saying. So you have sigma true versus epsilon true, the stress strain curve, let us say for a simple tensile test. So you do the tensile test, and somewhere over here you have the UTS. Remember, this is true stress, true strain. So the curve does not come down, it keeps on increasing. Remember, the load will keep increasing. So after the UTS also there is increase. We are not we have not talked about the real equation that will describe this, but the curve or the actual stress will keep on increasing. Let us not get into the details of that, but the stress is increasing, that is all is suffice to say. Now this true stress, true strain plot that we obtain from a uniaxial tensile test is representative of any kind of deformation that you give in the material. All you need to do is get effective stress value from there and effective strain value from that particular deformation, and that will be represented by this same graph, by the same plot. So the effective stress and the effective strain plot would be the same, exactly same as that you obtain by uniaxial tensile test. So the sigma true, epsilon true for a uniaxial tensile is same as the sigma epsilon and sigma bar or the sigma effective and strain effective for any kind of deformation. So that is the importance of putting in these numbers 1 by 2 and 2 by 3, because it is because of this we do not have to put any factor. Otherwise, what would have happened if there were no factor over there? You may have ended up with a factor on this sigma bar with respect to sigma true, and therefore, although the form of the curve would have been same, it would have been shifted or it would have been multiplied by some factor. But since it is a constant value, why not start with our definition such that these two overlap? So that was the idea behind putting on these factors. So that is like I said, a very important relation that we obtain, and this is again, do not forget that we are obtaining all this under von Mises criterion. We are not dealing with Tresca, because I said like I said that the effective strain relation that is given for Tresca is not supported empirically. So it is not dealt with, or it is not studied or researched to that extent. Now let us get to another aspect of this, which is, now we have looked at the stresses, strain, effective stress, effective strain, and how our true stress, true strain plot of a tensile curve can also represent the deformation under multi-axial stress strain condition. So, that part is covered. Now, we are in a very good position to be able to predict what will be the stress or what stress will be required for a given strain. Okay, so, that is done, but now what you would see is that there is even let us say somewhere over here you get yielding. You may not have thought about it so much in depth earlier, but now look at it and realize that at this point, at this whatever strain, if you look at it over here, it is 0.2%. So, beyond this 0.2% or whatever strain, if you look at it subtended over here, once the plastic material has started deforming plastically, you still need to increase the stress. So, that is something very intriguing. We will not get into the why of that, but let us understand a few basic things about it. It is first of all, it is called work hardening. So, whenever metals are plastically deformed, it is called cold working. Provided the temperature is less than 0.3 Tm. I have not yet described what is Tm, but this is melting point and we are more interested in the homologous temperature. We will get to those things a little bit later on, but for now just realize that when the temperature is less than 0.3 Tm, which is the melting point of the material. So, 0.3 times of the melting point of the material, and if you are deforming it plastically, then it is called cold working. Now, when you are doing cold working, what happens is that strength, and this is for to understand it in greater detail, you need to understand mechanical behavior of materials, but we are not getting into those details in this particular course, because it is altogether a different subject, but we will just give you idea enough so that you can apply it. Now, strength of a material and there are several increases when you when it is work hardened or when it is cold worked. There are several types of things that goes on because of which the strength increases. So, that is why I am saying we are not getting into the whys of it, we are just looking at what happens, and this is what we call as work hardening. So, the more the material is deformed, higher is its strength. That is what work hardening would mean in summary. So, if you have deformed it to 20%, it has some higher strength. If you deform it to say 40%, it will have even higher strength. Strength meaning if you do the tensile test, you will get a yield strength value which is higher. So, that is what it means. Now, let us look at it in terms of a plot. Again, so let us say again we are doing, now we can do simple tensile test, but of course, we know that it has greater significance. It will also imply the deformation behavior of at under a multi-axial condition. So, when I say uniaxial tensile test, we cannot think of it as just one simple experiment. It is representing the stress flow behavior or the stress strain behavior under all different kinds of deformation. Now, let us say this is the point which is we call as yield strength. So, this is the original yield strength of the unyielded material. So, I am using a term annealed. Okay, what it means is that the material is not at all deformed. You whenever you heat the material at a very high temperature, which is called as the solutionizing temperature, and you bring it back to the room temperature, then that material is in annealed condition, and in that condition it does not have any effect of previous cold working. So, even if you may have done any kind of deformation, that effect does not carry over if you have done annealing. So, let us say we are starting with a material which is annealed. So, now it has no history or it does not show any behavior from its past deformation. If you take the material from over here to here, which is the elastic region, and leave it, it will come back. We know that it is because of elastic properties, that is the elastic behavior of the material. Beyond this, which is we call as the yield strength, if you the material starts to show plastic behavior, meaning if you take it up to here and then leave it, it will come back, but it will have some remnant deformation. So, this amount of deformation will remain in this. Now, if you try to deform this material again, do not expect the material to go through this cycle again. What it does is actually it goes through. So, here the material, now if you start to deform it again or you start to apply stress again, the material follows this curve actually. So, what it is saying is that if you now leave this at this particular point somewhere over here, it will come back. So, it will have elastic behavior all the way up to this point, and it will get into the plastic mode only beyond this point. So, it means that the yield strength of the material, I will call it 2, and over here I will call 1. So, the yield strength of the material has increased. This is what we meant when we said work hardening. This material has been left with so much of plastic deformation. So, now when you try to deform it, you will need additional or a higher amount of stress to deform it, to be able to plastically deform it, and this is what is called this additional amount of load or stress that you need to this is what is called as work hardening. Now, once we know this work hardening behavior, there is a related concept which is called flow behavior or flow curve. It is nothing but just plotting or just explaining the behavior only in the plastic portion of the material. So, what we are talking about is flow behavior. The term flow actually comes from the fact that when you are deforming the material plastically, it does not come back. So, it flows, it does not, it has a behavior similar to that of, you can say, liquid or semi liquid. So, it does not come back, it will, once you have deformed it, it remains in that shape, or it it has moved ahead. That is what we mean when we say flow behavior. What it is basically plot of change in yield stress. So, you saw that the yield stress is increasing. The increase in the fact that the yield stress increases is called work hardening. Now, if you plot that yield stress, or you take the loci of that yield stress with increasing plastic deformation, what we get is called flow curve, and this behavior is called the flow behavior. It is called flow behavior because it gives stress required to make the material flow plastically. So, it is not flowing in the sense of liquid exactly, but you can say there are some characteristics similar to that, and which is why it is called flow curve. So, it gives the stress required to make material flow plastically. Now, if you remember our again the old stress strain curve, it had elastic region and the plastic region. Now, if we get rid of the elastic region, which is this one, we are remained with only the plastic region, and let us plot it over here, and we get something like this. And here it is plastic strain, no more just true strain. So, we are only talking about plastic strain, and this is the stress. So, actually it represents nothing but the yield stress for a given strain. So, let us say you have deformed the material up to this point. So, let us say you have deformed the material up to this point, strain 1. So, there will be a stress required to deform the material beyond this strain, and that will be, let us say, sigma 1, which is nothing but the yield stress at that point. So, sigma 1 is nothing but yield stress at strain 1. Now, what is the form of this equation? That will be very helpful for us. Then we would be able to predict the stress value, stress required, or the stress yield stress of the material after particular deformation. So, you can look at it in two ways. If you know the equation, then you can say that what will be the yield stress of the material, or you can say what is the stress required to deform the material up to that point, because you must be able to have stress at least up to that value, only then the material will deform to that point. And again, like I said, I have said it a couple of times earlier, if you are talking about the elastic properties, we have a very exact relation, that is given by Hooke's law. But if we are talking about plastic behavior, then we do not have a very exact relation, and here also we have one relation which is empirical, which has been obtained, you can say, based on empirical experiments, and which has some amount of you can say which has been verified to some extent by experiments, and it is called power law relation between the stress and the strain. So, what this relation is, it is like this. So, if you put this strain over here, you will get this stress over here. So, like I said, it is giving you two things. One, what is the yield stress after you have deformed it to this extent, and what is the stress you must be able to apply before you can get to this deformation. Now, there are again couple of things that you must be aware of when you are using this relation. Then you cannot apply it for very small strains. For example, never try to estimate the yield strength of the unyielded material from this by using strain equal to 0.2% or which is 0.002. It is not valid in that range. You will have to, you can say it is valid beyond something like 0.01 or 0.02. So, you cannot apply this relation below that strain, because as you remember, this is valid only when you are in the plastic strain regime. If there is any amount of elastic regime remaining in that strain, then this relation will not hold, and therefore, you have to be careful when using this equation. Now, this is called pre-exponential factor. and N is called strain sensitivity. Now we talked about what is the lower range where it is valid. It is not valid for very small strain. There is also the upper extreme or the upper limit where it is valid, and which is the UTS. You remember we have the uniform strain until UTS, and only up to this point we will be able to apply this. So, there is the upper limit is the UTS. So, one should be able to apply this in range between this. You can you cannot apply it for very small strains, but and you cannot apply it for very large strains, for example beyond UTS, because then the some of the assumptions break down. We are no longer in the range of uniform elongation or uniform deformation. Now, with that, let us look at some additional facts or how to deal with this power law relation in a little bit more detail. So, now we have sigma equal to k epsilon to the power n, but we also know that this is describing what? Our flow behavior from, let us say uniaxial tensile stress strain, and we also know that this sigma true epsilon true is also equal to sigma sigma effective and epsilon effective or strain effective, which is represented by the same curve. Therefore, this relation can now be also be written as stress effective is equal to k times strain effective times n. So, now we are in a position to also describe this relation for multi-axial deformation. Earlier when we wrote this, this was meant only for uniaxial stress strain condition, but now given the fact owing the fact that sigma true is same as effective stress and epsilon true is same as effective strain, we can write this relation sigma bar equal to k times epsilon bar. Now, let me write down an example. We will not solve it this time, I will give you time until next lecture. I will leave you with this example problem to think about. Plastic of a metal is given by sigma equal to 500 epsilon what is the yield strength of material cold worked to area reduction of R equal to 0.3, meaning 30% reduction in area, and you can assume something like a wire drawing operation. So, given this relation, find out the yield strength of the material. Yield strength meaning nothing but apply this after finding the strain value. So, once you are able to find the strain value, you can find what will be the stress, which is the yield stress after such deformation. So, try solving it and we will solve it in the next class. So, once if you are able to solve it, then you will be, or at least you try to solve it, it will give you a good feel of the numbers. So, we will see you in the next class. Thanks.